I'm going to talk to you now about the quantum universe to give you a frame in terms of the smallest and the largest. The smallest is described by the Planck unit. The largest is described by the event horizon of our observable universe, which is the interior of a black hole. Let's talk about these sizes with regards using a photon as a descriptor. So a photon, the shorter its wavelength, the higher its energy. The longer its wavelength, the lower its energy. I want you to imagine a photon with the shortest possible wavelength, basically the Planck wavelength. Now put it at a distance that is just inside the event horizon of our observable universe black hole. If you're on the opposite side of the observable universe black hole and you try to observe that photon, because of the expansion of space between you and that photon is described by the Hubble parameter, that photon will be maximally redshifted. Its wavelength will be maximally elongated to the longest possible wavelength permitted by our black hole universe. What is that longest possible wavelength? It's approximately 2 times the diameter of our observable universe. Those are the bounds. The upper bound, 2 times the diameter of the observable universe, and the lower bound, the Planck length of our quantized universe. It's not infinite. Thank you for listening to my dream about the quantized universe. I'm going to show you the math behind the quantized universe now. The smallest quantum is defined by the Planck length, which is 1.6 times 10 to the negative 35th meters. The largest quantum, I certainly used to believe the largest quantum possible in our observable universe was infinite. But now I know that's not the case. Our observable universe has a boundary. We are within a black hole. You can think about the observable universe as a resonant cavity, and in that way think about what is the largest wavelength which can stably resonate within that cavity. And the answer is a wavelength 2 times the diameter of that cavity. So think about our black hole universe in that regard, with our diameter being 8.8 times 10 to the 26 meters. So that suggests the largest possible wavelength which can stably resonate within our black hole universe is 1.76 times 10 to the 27th meters. Now the dream I had was to take a photon with the shortest possible wavelength and place it at one edge of our black hole universe, and then to observe it from the opposite edge of our black hole universe. And we know that space and time in between the observer and the source are expanding. That redshifts, which is also known, you could think about it as elongating the wavelength of that photon. So we start with a photon of the smallest possible wavelength, and we end at the other end of the observable universe with that same wavelength has now transformed into the longest possible wavelength through the Doppler effect and the expansion of space and time. This equation here is the relativistic Doppler effect. This describes how through space and time, a very distant photon has its wavelength slowly elongating. Now, the thing to notice in this equation, or to remember first, is that we're talking about a Doppler effect with something moving away from us. So the value we're going to be plugging into v for the velocity of the source away from us is going to be a negative sign because it's moving away from us. So c is the speed of light. These are the wavelengths. We can see this top here. We're going to have negative v over c, and v is going to be getting very close to c. So we're basically going to be ending up with approximately negative 1 here. Minus a negative 1 turns into plus, so 1 plus 1. We're approaching a 2 on the top side. On the bottom side, negative v over c, this is approaching negative 1. 1 plus negative 1 is approaching 0. Approaching 2, approaching 0. So a very small number here, and a finite number here, 2 approximately. 2 divided by a very small number is going to be a very large number. How large? Well, the redshift we're looking for is to take this wavelength, approximately the Planck wavelength, 1.6 times 10 to the negative 35th meters, and redshift it all the way to 1.76 times 10 to the 27th meters. That huge redshift is a factor of 10 to the 62nd. But because of the hyperbolic nature of this function, it approaches infinity but never gets there. Because of that, it is possible to achieve this factor of Doppler redshifting with the relativistic redshift equation. When I solved this, it's kind of funny. So it ends up being 99.999999999, and I had to stop in terms of being how close to the speed of light it is. 99.999999999, a few more nines, percent of the speed of light is the velocity you need to plug in here to get a redshift of that factor. But you can do it. The universe does it. Now the next thing we use, we know basically from that equation that I just showed you that we can assume we have to get essentially to the speed of light, that the expansion of space and time between the source and the observer has to be approximately the speed of light. So, to get that velocity, what distance of space and time is needed to achieve that expansion of space and time? The Hubble parameter defines that. Space and time is expanding at 70 kilometers per second per megaparsec. A megaparsec is 3 times 10 to the 22nd meters. This parameter, when you solve it out, you get 2.3 times 10 to the negative 18th meters squared per second. So now let's see, what does the distance between the source and the observer need to be to get the expansion of space and time at that factor? So the velocity, we said already, is going to be the speed of light. The Hubble parameter we have here in meters, 2.3 times 10 to the negative 18th meters squared per second squared. So speed of light in meters per second. Hubble parameter in meters squared per second. We solve that for d. We get 1.3 times 10 to the 26 meters. And now if you remember from the first lecture, this is the same order of magnitude, 10 to the 26 meters, and nearly the same number, off by a factor of a bit, a little wiggle room. But this phenomenon is very interesting in that it shows the quantization holds given the parameters we've observed within our observable universe.